Now that we know how to calculate the determinant, we should look at some specific examples. In this lesson, we're going to take a look at when the determinant is equal to 0. Take a look at matrix M. The determinant is 12 minus 12, or 0. But what does this matrix actually do as a transformation matrix? We should probably take a look at the images of several input points. The first point, 0, 0, remains 0, 0 after transformation. This makes sense based on the fact that M is a matrix of linear transformation in 2 dimensions. The point 1, 0 ends up at the image location 2, 4, making sense again that it is the first column of the matrix. 0, 1 ends up at the point 3, 6, because again, it's the second column of the transformation matrix. The point 1, negative 1 ends up at negative 1, negative 2 via multiplication. But so the same thing happens to the point negative 2, 1. It also ends up at negative 1, negative 2. We should also start to notice that these points seem to have something in common, and that is the fact that they all lie along the same line. No matter what point we pick in 2 dimensions, the image after the transformation matrix M will lie on this line. M maps all of 2D space to a single line, and we can see that the equation of this line is y equals 2x. So let's think a little bit about why all the points in this matrix map to the line y equals 2x. We saw visually that all the points ended up on that line, but what about the matrix yields this result? We should then think about what this matrix would look like as a set of transformations. This matrix takes a pre-image xy and yields some image x prime y prime through multiplication. If we turn this back into a system of 2 equations, we see we have the equation 2x plus 3y equals x prime and 4x plus 6y equals y prime. We can also see that the equation for y can be factored. We can factor out a 2 and get 2 times 2x plus 3y equals y prime. Well, do we have anything that's equivalent to 2x plus 3y? We sure do. It's equivalent to x prime. So we can rewrite this relationship as y prime is equal to 2x prime. What this means is for every x prime, every image x, its y-coordinate is twice its x. We drop the primes because we're just talking about where the line lies in space, but it really refers to where the images lie in the 2D plane. In the last example, we found that 2 different points yielded the same image point, negative 1, negative 2. So what if we wanted to find all the points whose image was a certain point? Well, we would be wanting to solve the system where the matrix times some pre-image point xy yields the outcome negative 1, negative 2 in this example. Well, we learned how to solve a problem like this using matrices. We can use the augmented matrix, which we've set up here. We can start to do row reduction by subtracting 2 row 1s from row 2, and what we'll notice is we get a matrix with the bottom row of all zeros. We could continue using matrix row reduction or Gauss-Jordan, but we actually already have it basically as simplified as we can. So we can turn that top line back into the equation 2x plus 3y equals negative 1. So any point along that line, 2x plus 3y equals negative 1, the image from the transformation would be negative 1, negative 2. Suppose now the question we are trying to answer is finding all the points whose image is the origin. Therefore, we want to know the matrix times some vector or point xy yields the origin, or we say maps to the origin. Again, we can set up our augmented matrix system. We can subtract 2 row 1s from row 2, and we get this matrix 2, 3, 0, 0, 0, 0. Again, we could continue and multiply the top row by a half. We can already turn this back into the equation 2x plus 3y equals 0, or y equals negative 2/3 x. So that means any point along the line y equals negative 2/3x will map to the origin. This concept is called the null space or kernel of a matrix. The null space is the set of all points that map to the origin. Kernel is just a synonym for null space and the inspiration for the name of this channel. Now suppose we're thinking about mapping all of 3D space to a line instead of just 2D space to a line. Take, for example, the transformation matrix 1, 2, 3, 1, 2, 3, 1, 2, 3. We can convert this matrix back into transformation equations x plus 2y plus 3z equals x prime, y prime, and z prime. We should quickly notice that the equations for x prime, y prime, and z prime are all the same. Thus, we can make the conclusion that x prime is equivalent to y prime and z prime. We've seen earlier that if we set this equal to some independent parameter t, we can rewrite the equation of x, y, and z in terms of t. Thus, we get the equation of a line x, y, z equals 1, 1, 1 times t. This is called the image space of a transformation because it refers to the fact that all the images lie in this space, which in this case is a line. We can also ask ourselves to find the kernel or null space of this transformation matrix, which is answering the question, the matrix times what x, y, and z values yield the origin. After setting up the augmented matrix and performing row reduction, we are left with just a single non-zero row, 1, 2, 3, 0, which we can convert back into an equation x plus 2y plus 3z equals 0. That's our null space. It's the equation of a plane. So the image space was a line and the null space was a plane. Let's just recap some things we've seen so far in this video. All of the things we've talked about today apply when the determinant is equal to 0. The null space, or kernel, is the set of all points who map to the origin. The image space describes where all images end up after multiplication by a transformation matrix. When the determinant equals 0, we say that a transformation loses dimension. Here's an example. If all of 2D space maps to a line is a one-dimensional object. Thus, we've gone from 2 dimensions to 1 dimension, and 1 dimension has been lost. If the image space of a 2D transformation is a line, its null space is also a line. If the image space of a 3D transformation is a line, its null space is a plane. If the image space of a 3D transformation is a plane, its null space is a what? We haven't seen an example of this yet, but next time we'll take a look at the transformation in 3D, which image space is a plane and null space is something else.